be the motivation for my whole approach. Indeed, you may recall from information geometry the basic example of the information metric of the univariate normal model, which up to a slight change of coordinates is the same as the Poincare half-plane metric. So we have a striking connection between, on one hand, a fundamental object in statistics, and on the other hand, what is a fundamental example of a Hadamard manifold. We may accept this at face value as a fact, but of course, psychologically, we would like to ask why. Where does this come from? Is it a coincidence? And I'm going to argue that no, it's not a coincidence, it's a consequence of the fact that this information metric is what we call a warped metric. So look at the information metric. Whenever you see Z, it will be the couple X bar sigma. The information metric looks like a product metric. It's a sum of squares. But in addition to that, you have these coefficients like sigma to the -2 that depend on sigma, not on X bar. Roughly, this is the definition of a warped metric. And we will see the same remains true for a large class of location scale models. The information metric is a warped metric. Then our intuition is that the negative curvature in this example is only an instance of the general principle that you see written here. Warped products use convex functions to generate negative curvature. So in order to implement this intuition, I will follow a strategy, which is to replace the univariate normal model with its parameter space, which is the half plane, by any location scale model defined on a Riemannian manifold. So the parameter space will be a kind of visually a generalization of the half plane, except the fibers, they are copies of the manifold M instead of being horizontal lines. The question is, will the information metric down here continue to be a warped metric? In other words, does this square commute? And the answer is yes. This is the new theorem I was telling you about at the beginning. It says if M is in a reducible symmetric space, and if the location scale model is invariant to isometries in the sense of this condition, then the information metric is indeed a warped metric. Moreover, we know the precise expression of this metric, written here in blue, with coefficients alpha 2 and beta 2 that are given by these expectations. In appearance, these involve X bar through Z. However, they only depend on sigma, so they are well-defined functions of sigma. The proof of this theorem, which you can find in the extended version, is an application of Schur's lemma from the theory of group representations. And if you don't like the condition that M is irreducible, you can drop that condition. So then instead of a warped metric, you will get a so-called multiply warped metric. Having established this, I would like to digress a little bit and mention some general properties of warped metrics in order to then apply them to a specific example. So to begin with the definition, we are looking at a space that is a product space, just a Cartesian product. The half-line 0 infinity is called the base. The manifold M is called the fiber. Each one of these two has its own Riemannian metric. But then in addition to that, we have the function beta that appears in the metric here in order to warp or deform the metric of M. So we get a Riemannian manifold, which I call cursive M of beta. Now, this is only a special case of the definition of a warped product or warped bundle, but I won't go into that. So since the half-line 0 infinity is one-dimensional, any metric is a Euclidean metric. It's dr squared for some function r. And the significance of this r visually is vertical distance. If you have 2 points on the same vertical line, the distance between them is the difference in r. Let's look at this table, though, which is quite interesting. So as I said, warped metrics, they appear in geometry and in physics. And then the quantities r and x bar have different interpretations. For instance, in geometry, r is a distance function. It's the solution of a Hamilton-Jacobi equation. And x bar is a fiber point. Well, in physics, you have some other interpretation too, right? And what we would like to see is a new vision of warped metrics, which is a statistical vision, where r means dispersion and x bar means location. So we introduce a statistical vision of this mathematical object. Onto something more technical. In fact, the completeness and curvature of warped products is characterized analytically. For instance, M beta is complete if and only if both the fiber and the base are complete. Completeness of the base is equivalent to divergence of both of these integrals. The first integral is distance to 0, and the second integral is distance to infinity. So if they are both infinite, it's impossible to escape, neither from the bottom nor from the top. Hence, hence completeness, I'm sorry. For curvature, any sectional curvature can be found either from the Gauss equation or the Jacobi equation. If you look at the Gauss equation, if beta is a convex function of R, meaning it's geodesically convex, then we have negative radial sectional curvature, and this is the principle that convex functions produce negative curvature. Let's go on with our example, the von Mises-Fisher model. This is only an example among others. However, I chose what I thought would be most familiar to the greatest number of people. I hope I'm right in doing that. So here the fiber is the unit sphere, M. The model is an exponential model involving the Euclidean scalar product of x and x bar, and eta is strictly positive. So our parameter space is the product of a sphere and a half line, meaning it looks like the space Rn punctured at the origin. We don't know yet whether we can include the origin or not, but statistically the origin corresponds to the uniform distribution on the sphere. If we look at visually at our parameter space, the spheres become larger as we move away from the origin. And this is also statistically correct because eta is a concentration parameter. So as the densities become more concentrated, they are farther away from each other. So back to the question to what happens at 0, the coefficients of the metric, which we can find from our theorem, they are given by modified Bessel function. And if we take their functions and if we take their limit at eta equals 0, we see the limit value of the metric does not depend on the direction along which we converge to the origin. And this means the metric extends by continuity and even extends smoothly to the origin. And in conclusion, we have a bigger Riemannian manifold, which I call M hat. This is the whole of Rn, with the origin included, and equipped with the information metric. And we are going to see that this is a Hadamard manifold. So to begin, it's simply connected and it's complete, unlike the punctured space. Indeed, for simple connectedness, well, Rn is simply connected for any value of n. However, notice that for n equals 2, if we exclude the point at the origin, we lose simple connectedness. So you already see the importance of including the origin. Going on to completeness, we have our two integrals, distance to 0 and distance to infinity. The first integral converges, in fact, and this means that it is possible to escape our parameter space M at 0. But this isn't a problem because M hat contains 0, so that's not a problem for the completeness of M hat. The second integral diverges because we can look at an asymptotic expansion of alpha 2 as eta goes to infinity as a power series of 1 over eta. The first coefficient A is 0, so we cannot decide. The second coefficient B is also 0, so we cannot decide. And our last chance is the last coefficient. And luckily, this is non-zero, so we have logarithmic divergence of our integral, the distance to infinity. And this shows that M hat is complete, right? But M is not complete because the distance to 0 is finite. So we can now look at the curvature of M hat. So experimentally, we have seen that this curvature is negative. So indeed, M hat is a Hadamard manifold. Symbolic and numerical experiments have produced the same result to the effect that the sectional curvatures, well, for any value of n that we have looked at, n going from 2 to roughly 12, 10 or 12, the tangent and radial sectional curvatures have this negative profile, which decreases to a limiting value. So this is very pleasing because we can now see the space is indeed a Hadamard manifold. But of course, the question is why. In other words, how could we prove this? We have made an additional experimental observation that as eta goes to infinity, all sectional curvatures become equal. So our space starts to look like a constant negative curvature space. And it should be clear this is a manifestation of the central limit theorem. So statistical intuition, as eta goes to infinity, because eta is concentration, the model starts to look like a normal model. And the information metric of a normal model is a hyperbolic metric. It has constant negative curvature. So what we are seeing is interpolation between the uniform distribution at eta equals 0 and the normal model as we tend to eta goes to infinity. Again, eta is a concentration, not a dispersion parameter. So this kind of reasoning is general. Whenever you have a concentration parameter and a central limit theorem, the curvature interpolates between the two. So very quickly, there's also a full analytic solution of the geodesic equation. To find this full analytic solution, you look at conservation laws of energy and moments. And then you have a lemma here, which allows you to lift the whole problem to the Lie algebra of the group of isometries. As a result, the geodesic is separated into R, which follows a one-dimensional mechanical system, and X, which is a time-changed geodesic in the manifold M. So we know how to construct geodesics without any numerical computation in the warped product space. Now, as an aside, as a remark, a similar construction holds for Brownian motion in the warped Riemannian metric. And that's interesting because in the same way that we use natural gradient descent, we can also use natural diffusions to realize optimization. So it's good to know how to build a Riemannian Brownian motion. In future work, our goal will be to develop the applications of this formalism. So the first application to density estimation, my colleague Yannick Berthoumieux will give a full talk about tomorrow. I will try to summarize the remaining three. To begin with regression, let's assume we have a learning sequence of inputs, xn, which belong to some input space, anything, and outputs, yn, which belong to the manifold M. To learn the relationship between these two, we start from a learning model where y is concentrated, is about some image, y bar theta of x, according to a location scale model. And the learning this image is controlled by a parameter theta that is unknown. The learning problem is to find the best theta. So following the principle of empirical risk minimization, we want to asymptotically minimize the Kullback-Leibler divergence between the truth and the model. And this leads us to this cost function here. Now, what we know how to do is that we know how to compute the information metric of the learning model. And this turns out to be the average of the pullback of the warped metric. So we know the information metric of the learning model. And as a result, our problem reduces to stochastic optimization on a Riemannian manifold, which moreover is given its information metric. So we have good convergence properties with regard to efficiency. For the second application, we consider natural evolution strategies. So this is a problem of black box optimization on the manifold M. This means the cost function f is difficult to evaluate. The main idea is to implement search distribution which expresses our belief about the position of minima. Naturally, we take this to be from a location scale model. And then the core idea of NES is to replace black box optimization by classical optimization because we minimize an expectation or other probabilistic construction instead of minimizing f itself. So because we know the information metric, we have computed the information metric and we know it's a warped metric, we know the expression of the natural gradient, duality with respect to the warped metric, and any derivatives that appear don't imply the derivatives of f. And we can fully implement Riemannian gradient descent, meaning natural gradient descent, because we know the metric already, we know how to compute gradients, and we know how to construct geodesics. Exact solution of the geodesic equation. So we're quite good with doing solving this kind of problem. And this generalizes known evolution strategies like CMAES to manifolds, to black box optimization on manifolds. I don't know if I have enough time to... All right, that's good, that's enough. Third application would be averaging of clusters, yes? So a cluster is a sample from a unimodal data population. So if we have some clusters like here, we can map them through maximum likelihood estimation to points in the parameter space of our location scale model. So if we ask the question, given several clusters, what is the average, most representative cluster? For instance, because we have too much data and we want to get rid of it, This amounts to finding a Riemannian p-barycenter in the warped product manifold M beta. Yes? So we can solve this numerically thanks to geodesic shooting. Remember, I have shown you we know how to solve the geodesic equation for initial conditions. We don't know how to solve it for boundary conditions, but we circumvent this by implementing the technique of geodesic shooting, because luckily we know geodesics and we know curvature, so we have no problem in solving this kind of problem, the average cluster, or in finding the distance between clusters, using also geodesic shooting technique. So now I would like to thank you for your attention, and this is a summary of some of the main points, and please go ahead with any questions. Thank you. Yeah.
So what is the computational efficiency of the geodesic shooting?
I'm not sure how to answer you. In geodesic shooting, well, I think the computational difficulty coming from constructing geodesics with given initial conditions is very weak, because we know analytically how to solve the geodesic equation with initial conditions. Now, each time we need to solve the Jacobi equation, and this is a linear second-order differential equation, so I guess because it's linear and we have well-known methods for solving like Runge-Kutta or anything, then it shouldn't be difficult to solve. I still would imagine, although there are people here who know this much better than me, like Alice, but I still would imagine on a laptop computer, it wouldn't run for too long. It would maybe take not more than, just a regular runtime of some. Yep. Yeah. Thank you.
So good morning, everyone. So this is a joint work with my colleague Richard Nock, and this is about a generalization of Bregman divergence using an extension of convexity, ordinary convexity, that is called comparative convexity. Okay, so let me recall you the ordinary background. So with the notion of convexity and Jensen and Bregman divergences. Okay, so in 1906, Jensen introduced the midpoint convex property of a function f, and it is said that f satisfies the midpoint convex property if we have this inequality here. And any continuous function having this midpoint convex property also satisfies the common convexity property for any lambda here. And moreover, when this inequality is strict for distinct point and lambda in between 0 and 1, then we have the strict convex property. We should be careful, because if you only have the midpoint convex property and not the continuity of the function, then it may not be convex. So you have some examples that are reported in former papers. So a divergence in information geometry can be said as a smooth dissimilarity measure. And we say that the divergence is proper if it satisfies the law of the indecinables. And from the Jensen inequality, we can design a divergence by taking the right-hand side minus the left-hand side. And we design the Jensen divergence as follows here. And we can, moreover, instead of taking 1/2, just take for any alpha between 0 and 1 and have the skew Jensen divergence here, where we have some kind of symmetric relationship between the reference points written here. So this is a traditional framework. And of course, in information geometry, the canonical divergences of dually flat spaces are Bregman divergences, where the formula is recalled here. And we know that Bregman divergences can be interpreted as the limit cases of scale skew Jensen divergences here. So this has been shown by Zhang in 2004 and other people. So a geometric interpretation of the Jensen skew divergence and the Bregman divergence is as vertical gap when you plot the convex function. Here you will have the skew Jensen divergence as a vertical gap between the chord and the point at the function, and you will have the Bregman divergence as a vertical gap from the point of the function at P with the point evaluated at the tangent plate emanating from Q evaluated at P. Okay. And of course, when you scale that, they become, in the limit case, similar. So now let me introduce this generalization. We are going to define what is comparative convexity. And the idea is to define Jensen divergence with comparative convexity and to take the limit to define a generalization of Bregman divergences. Okay? So for that, we are going to use not arithmetic means, as it is usual, but abstract means function. So a mean between two scalar values, P and Q, is contained between the extrema, so between the mean and the max. And we will say that a function, by definition, we will say that a function f is midpoint Mn convex if and only if it satisfies this inequality here. So basically, you can see that if you take the arithmetic mean for M and N, you recover the usual Jensen midpoint convexity. Okay, so this is just a generalization by introducing means. Okay, so now means can have various properties, and we will require the means to have a special property that we call regularity. So let me introduce you what are regular means and to give some examples of regular means and non-regular means. So we say that a mean is regular if it satisfies the following four properties. It should be homogeneous, so for a positive constant lambda, it should be 1 degree homogeneous. It should be symmetric, continuous in each variable, and also increasing in each variable. So if you take the power means or the Holder means, which are defined in this equation, and if you by a limit case you take P0 to be the geometric mean, then you have for delta belonging to R a smooth family of order means. Then those means are regular. They satisfy those four properties. And the power means are just an example of something that is called quasi-arithmetic means, also called Mogorov-Nagumo definitive means. And the quasi-arithmetic means also satisfy those properties, so they are regular means. Okay? And they include the very famous Pythagorean means, arithmetic mean, geometric mean, and harmonic mean. Okay, so you have many kind of ways to construct means and weighted means. You have, for example, construction by mean value theorem. So then you have Lagrange and Cauchy means, Stolakis means, and all those means are regular. So there are families of regular means, but you also have families that are non-regular. For example, the Lemmer means. Okay, so not all means are regular. So now the property of having a regular means is going to help us to guarantee that the generalization of skew Jensen divergence will be proper. And this is, so if we take Mn midpoint convex property F and that the mean are regular, then the skew Jensen divergence will be behaving well. They will define the proper divergence. So we consider an extension of means by putting some weights, 1 minus alpha alpha, and we define the Mn convex property of a function f as follows. So instead of having arithmetic mean, you put M and N, okay? And basically, we again have the fact that if it is continuous function and midpoint convexity, then you have the Mn convexity property for any alpha, okay? And this allows us to define the generalization of a skew Mn Jensen divergence by taking the difference between the left-hand side and the right-hand side with still the symmetric properties that holds. So now the key idea to get a generalization of Bregman divergence is to take a limit argument by taking alpha going to 0 and 1 and to see if that limit exists, what will be the generalized Bregman divergence for Mn convexity. So this is the definition of a generalized Bregman divergence. We just, as I said before, define them as limit cases when alpha tends to 0 or 1. And for having a proper generalization of Bregman divergences for Mn convexity, we need to prove that the limits exist and also that the Bregman divergences are proper, okay? That satisfies the law of indecidability. And if you take quasi-arithmetic means, which are regular, we end up for scalar divergences, we end up with this formula here, okay? And this formula, if you take tau to be the or an rho to be the identity function, you recover, of course, the usual Bregman divergence, but you can get for any pair of quasi-arithmetic means a generalization of a Bregman divergence. Okay, and the proof, I'm not going to go into details, is by taking first order Taylor expansion of the weighted means, and you will find that weighted quasi-arithmetic mean first order approximation is that, and then you will look now at the second term with f of another weighted mean, and you will take again first order Taylor expansion, and in the end you will find that this is this expression. So now what we have to do is to prove that those divergences are proper. So if we take another function j, and we define j to be the composite of tau, f, and rho minus 1, then by taking the derivative, we get also, this is a convex function, and then we get this expression of a divergence here. And what we have is that we have the fact that our rho tau generalization of Bregman divergence is just a scaled version of an ordinary Bregman divergence on the rho representation. And this proves that our divergence, rho tau generalized Bregman divergence, is proper. Okay. So now we can instantiate it for power means or Holder means. We just choose the rho and tau as a polynomial of degrees delta 1 and delta 2, and we end up with this formula, and we can check when the delta 1 equal delta 2 equal 1, then we get the usual scalar Bregman divergence. Okay. So now we need to check whether a function is Mn convex or rho tau convex, and this test can be done as a usual convexity test on a composite function. So you will say that f is rho tau convex if and only if tau rho f rho circ inverse of rho is ordinary convex. Okay, so this is a very easy proof and very well-known proof from I think the 60s by Axel. This is just here. You just have to consider that tau is increasing function in that case, not only monotonous but also increasing. And you just plug the things, and you will have this equivalence between rho tau convexity and ordinary convexity on the transform composed function here. Okay. So let me summarize the contribution of this work. We have introduced a new generalized notion of skew Jensen divergences, and by taking limit arguments, we introduce generalized Bregman divergence. And the notion we use for doing that is to play with comparative convexity. And we got some new formulae for quasi-arithmetic Bregman divergences and a subfamily of it that are power mean Bregman divergences. We can interpret those divergences as a conformal divergence, so a scaling factor of an ordinary Bregman divergence, which shows that it is proper. And I think this work emphasizes on the fact that weighted regular means are also at the heart of dissimilarity function and divergence. And we can also use other notion of means to define other kind of generalization. For example, by taking comparable means, when you can compare families of means that you can compare, you can introduce a new generalization of Bhattacharya statistical distance. This is not explained in these slides, but you can have a look at archive. So I just want to conclude by some kind of maybe philosophical question. When we have information geometry from a convex function, we can introduce a dually flat space with a canonical divergence that is a Bregman divergence. But convexity, ordinary convexity, is up to affine transformation, which is an extrinsic. So from an extrinsic function, we build an intrinsic geometry. And here, by taking a generalization, we want to better understand what is the embedding of data, what is the role of means in the construction of information geometry. So I think there will be ongoing work in that direction. So thank you.
Thank you. Thank you. Maybe you know that Chento's characterization gives the unique Riemannian metric and dualistic affine connections. And any divergence function also associated with one Riemannian metric and two affine connections. Can you characterize your class of divergence function is characterized in the sense of such a differential geometric idea?
This is very interesting question and fundamental questions that need to be answered for sure. So I think there are two elements of an answer. The first one is that for any divergence, as you work, we can build a dually structure by taking second and third order derivative. So this should be computed and see what kind of dual connection we have, coupled with the metric. Yeah. So this is just calculation that should be done on that. I have no answer now because I didn't do the calculation yet. Mm-hmm. And the second part of my answer, which is more interesting but very difficult, is that Chenkov used category theory and Markov morphism on finite discrete sample space to prove unicity of Fisher information and alpha connection. But even in the continuous case, and the things are more delicate, and it will be nice to see what is an axiomatization that leads this kind of divergence. This I have no idea now, but maybe you can give me some hints at that, I guess.
Yeah, thank you.
Thank you.
Any more questions? Okay, so we can thank the speaker again.
Okay, sorry. Okay, so let's start with the basics. The Shannon entropy of a random variable is the Shannon entropy of its distribution, namely, in statistical words, the opposite of the average log likelihood of the distribution. And similarly, the Rényi entropy of a random variable is the Rényi entropy of its distribution, which depends on some positive parameter Q, such that the Rényi entropy equals Shannon entropy when Q equals 1, and takes the following form when Q is different of 1. Namely, it is up to the multiplicative factor, the logarithm of the sum of the probabilities up to the power Q. Okay, we are interested here in entropy rates of sequence of random variables. If you are considering a random variable, the Shannon entropy rate of this sequence is defined as the limit, if it exists, of the marginal entropies of the sequence, that is the entropy, the sequence of entropies of the first marginals of the sequence, renormalized by the time unit, that is to say, multiplied by 1/n. And Shannon proved that for an ergodic Markov chain with finite or denumerable state space, this entropy rate has an explicit form precisely, it is expressed as the average of the entropies of the transition probabilities of the chain weighted by the stationary distribution. So it has many interest because this expression is explicit in terms of the transition probabilities and has some dynamic interpretation in terms of the dynamics of the chain. The original proof of Shannon relies on the following functional identity known as the chain rule, saying that the entropy of a couple of random variables can be split into two terms. The first one is the Shannon entropy of the first marginal, and the second one is the conditional entropy of the second marginal with respect to the first one. Namely, it is the average of the entropies of the conditional distributions weighted by the first marginal. So maybe the first guess for getting similar expressions for Rényi entropy is to try to follow this proof and adapt it to the Rényi entropy. It will work up to some additional work because Rényi entropy also satisfies some kind of chain rule in the sense that you have the same kind of decomposition for the entropy of a couple of random variable, except that that we will call here the conditional Rényi entropy takes the following form. It is some average of, say, some entropy of the conditional distributions, but the weights are no more given by the first marginal, but by one of its escort distributions, which are defined as here as the original probability distribution up to some power q and renormalized to get some probability distribution. And so if we want to adapt the original proof of Shannon to get some closed form expression for Rényi entropy rate, then we have to have a better understanding of the behavior of these escort distributions for a Markov chain. And this will require to study some perturbation of the transition matrix that I will introduce now and which has already been used previously to get some alternative closed form expressions for Shannon entropy rate and also Rényi entropy rate by Rached and its co-author in 2001. The idea is the following. You can express the Rényi or Shannon marginal entropies as explicit expressions of some Dirichlet series associated to the chain. Here the Dirichlet series is the following functional lambda of S, which is the sum of the probabilities of all words with length n to the power s. And here the relation is the following. The marginal Rényi entropy of the random sequence can be expressed as the logarithm of this Dirichlet series. And so to understand the behavior of the marginal entropies, you have to understand the behavior of this Dirichlet series, which can be written in the case of a Markov chain essentially as some power of a perturbed transition matrix. The perturbations consist in transforming all transitions by this power s function. Okay, so we have to understand the behavior of this transition, this new matrix P of S times to the power n minus 1. And so it is given by this behavior is given by essentially the Perron-Frobenius theorem, since P of S is an irreducible and a periodic matrix. It has a positive eigenvalue and positive left and right eigenvectors associated to this eigenvalue that satisfy the following properties. Following properties. The first one say that this positive eigenvalue is dominant in the sense it is greater than any the modulus of any other eigenvalue of the perturbed transition matrix. This is called the spectral gap, and the last property, called quasi-power property, says that essentially the Dirichlet series behaves as this dominant eigenvalue to the power n minus 1. And so, if you come back to the Rényi entropy, then you get that marginal Rényi entropies can be written as something linear with n, that is, its growth rate is linear in n, times some value here, the logarithm of the dominant eigenvalue. And so the entropy rate of Rényi can be expressed as the logarithm of this dominant eigenvalue. Okay, this is nice, but for application it may be not adapted, particularly if you think of maximizing this entropy rate under constraints on the transition matrix, because it is not expressed as an explicit expression of the transition matrix. So we were interested in obtaining some closed form expression, some explicit expression in terms of the transition matrix. And so we get something here. So this entropy rate for Rényi entropy is expressed here as the logarithm of something that can be interpreted as the average of entropies of the transition probabilities weighted by something, and this something is no more the stationary distribution of the chain, but the left eigenvector associated to the dominant eigenvalue of the perturbed transition matrix. This is closely related to the expression obtained by Shannon, in the sense that you have some weighted expression in both cases, and also if you are considering the first line, the first formula, when Q tends to 1, you get the second formula, and so the formula we obtained for Rényi entropy is consistent with the previous work. Okay, here I sketch some proof. One proof that consists in using the chain rule for Rényi entropy, the escort chain rule, and then the Markov property to get this expression. And it appears that the main difficulty is to interpret the red expression. And actually, this red expression is the marginal entropy of some marginal distribution of the escort distribution of the chain, and we get that this expression, this marginal converges in distribution to this left eigenvector of associated to the dominant eigenvalue of the perturbed transition matrix, and so we get this expression. There is a second proof that consists in more generally proving that the dominant eigenvalue can be itself expressed as this weighted expression in the logarithm. Yes, thank you. Okay, so maybe the next question is what about other entropy functionals? Okay, so we said for Shannon, for Rennie, and what for others? Well, according to me, the chain rule approach cannot be adapted in the general case because axiomatically Shannon is the only entropy functional that satisfies the original chain rule, and Rennie entropy is the only one that satisfies the escort chain rule, and so you have no way in this direction to adapt easily to other entropy functionals. But the Dirichlet series approach can be adapted, and actually we had, and we are able to derive closed form expressions for generalized entropy rates. And what do I mean by generalized? For other, I said for Shannon and Rennie, the growth rate of marginal entropies is linear with the number of variables. For other entropy functionals, you can have other behaviors. Some grows very fast, some grows very slow, some decrease, etc. And so you have to compensate this behavior to get some non-degenerated expression for the related entropy, but provided that you rescale by the good speed of convergence, then we get some expressions that I can show here in the table that sums up some results on other entropy functionals. Okay, you just have to look this column in which we gave the growth rate of the marginal entropies, and then in the following column you find the expression of the related generalized entropy rate following the Dirichlet series method. So I'll stop there. Thank you for your attention, and if you have any question, please ask. Yes.
So you can use only the Dirichlet series approach.
Yeah.
So you still have the problem of practical compatibility.
No, not exactly, because it's a good question. You're right. I understand your question. So here I gave the expression in terms of the dominant eigenvalue. So it may appear that it is not explicit, but generally we have these expressions for the dominant eigenvalue or its derivatives that relates it to the transition matrix. And so we are able to completely explicit the expressions in terms of the transition matrix, even for the Dirichlet series approach. Okay. Thank you.
Okay, thank you. This is a joint work with Frank Nielsen, and I will speak about multilinear algebra of tensor and asymptotic statistics. So the problematic of interest is the performance in terms of minimal base error probability for detection of a random tensor. This is a severely understudied problem because an analytic expression of the error probability is generally not tractable. Some related works are listed here. About the Chernoff upper bound, so the cube, and the error exponent in the doubly asymptotic regime. The doubly asymptotic regime means that the tensor sizes and the number of parameters of interest grow jointly in a control way. And we have to notice that this problem has been studied in the context of matrix, not tensor, but matrix-based sensing model by Boyer and Nixon. But the case of interest in this work is to derive the cube and the error exponent for random tensor following a higher order SVD decomposition. So we consider a standard equiprobable Gaussian distributed hypothesis detection test, and we will see that under the null hypothesis and the alternative hypothesis, the distribution is Gaussian, and only the covariance matrices are different. We define the error probability by two terms. The first term is the probability to decide the null hypothesis, and in the same time we know that the alternative hypothesis is right. And the second term is to decide the alternative hypothesis knowing the null hypothesis. And the detection test here is the log likelihood ratio test. So the cube is given by the expression on the top. So the error probability, which is defined as the expected minimum of two likelihood functions, is upper bounded by the cube, and the cube is the tightest upper bound for this error probability. And for over S, for over parameter S, we can obtain over relaxated upper bound as shown on the right. But the main objective here, for one of the goal, is to derive the S star, which is the best, which gives the best exponentially DC rate, and S star belongs to the interval 0, 1. So we define the error exponent for Gaussian hypothesis according to the Stein lemma. So the limit over n of the logarithm of the error probability divided by n. So this limit gives the error exponent, and we know we recognize that the S divergence mu is considered at the S star point, and we give here the S divergence, and we can see that this divergence is parameterized by the covariance matrix under the null hypothesis and the covariance matrix under the alternative hypothesis. So we consider here the canonical polyadic decomposition with random amplitude. This means that the tensor X is exactly the sum of R rank 1 tensor as illustrated in the graph. And so this is for Q for a free order tensor, the graph. And we consider amplitude SR as a random variable and indically distributed with a variance sigma S square. So we have to obtain the binary hypothesis test and the S divergence for the CPD model. By doing this, we vectorize the noise-free, the noisy tensor Y, and we build a matrix phi which is the Catril-Rao product of individual matrices phi q to phi 1. So based on this observation, on this vector, we have the binary hypothesis test. So under the null hypothesis, the SNR is equal to 0. And in this case, the observation vector follow a normal distribution with a covariance matrix equal to sigma square times the identity matrix. And under the alternative hypothesis, the observation vector for a SNR different to 0 follow a normal distribution with this covariance matrix, so sigma 1 here, and where we recognize the SNR and the matrix, the structure matrix phi. And finally, we give the S divergence for an observation vector of length n. And this is a log-det type divergence. So there is no figure. Okay. Normally there is 4 figures. Okay. Donc here we define the empirical spectral measure by Qn lambda, and this empirical spectral measure finally count the number of eigenvalue of the matrix phi transpose. So in the conventional case, R is fixed and n goes to infinity, and in this case, the empirical spectral measure converge to a non-random measure associated to the Dirac density. But in this work, we consider the non-conventional scenario due to Marchenko and Pasture. So we consider that R and n goes jointly to infinity with an aspect ratio, with an asymptotic finite aspect ratio. So R over n goes to C. So in this case, the empirical spectral measure converge almost surely toward a deterministic measure whose density is the well-known Marchenko-Pasture law. And the Marchenko-Pasture law is recalled by function f, and lambda minus and lambda plus is the support of the law. So, knowing the Marchenko-Pasture law, it is possible to derive a closed form to this expression here. So the log-det of this expression, and this is an important term in the Chernoff, in the S divergence. So this term converges to this integral, where we use here the Marchenko-Pasture law. So this is the standard framework, but recently we have extended this result to a structural matrix. So phi is structured in the sense that phi is the Catril-Rao product of individual matrices, phi q to phi 1. And in this case, this key quantity converge almostly to the function phi, psi c of x, and the function is given here. And this function is parameterized by C and by the support of the Marchenko-Pasture law. So based on this result, it is possible to give the S divergence mu S according to the previously introduced function psi here. Okay, so we have a simple expression, and we can obtain approximated analytic expression for a limit case. So This means that here we consider C much lower than 1. And in this case, the S divergence can be approximated to this very simple expression. Okay, and this expression is only parameterized by CS and the SNR. And we can easily deduce the stationary point S star according to this expression. And this expression is only a function of the SNR. So here we consider, we follow the same methodology as for the CPD, but we apply the methodology to the higher order singular value decomposition. So now we have to consider a set of orthonormal matrices, U1 to UQ, and the tensor, the Q order tensor, is the product, the n-mode product. So by a core tensor S bar, the first mode product by U1, the second mode product by U2, etc. So we vectorize the tensor Y, and by doing this, we compute a large matrix U, which is the Kronecker product of individual matrices UQ to U1. And we have also to introduce a projector P, which is defined as the product of U transpose. And this projector is the Kronecker product of the individual projector PQ, and PQ is defined here. So the main result on the error exponent and the optimal S parameter is given in this slide. So we modify the statistics test 2 in the sense that now we consider the alternative hypothesis given here. And in fact, we have replaced the product phi transpose by the projector P. And in this case, the error exponent and the optimal S parameter are given here. And it is interesting to remark that the approximation of the error exponent given by expression 3 in the here. So this is for C much lower than 1. In this case, this approximation holds exactly, and the S divergence is exactly equal to this simple expression. And in the same spirit, the S star, which is the global minimizer of mu S, is exactly given by expression 4. And so by expression here, which is very simple because this is only a function of the SNR. Recall the fundamental inequality. The error probability is lower bounded by the tightest bound, the cube, and another popular bound is the Bhattacharya upper bound, and we obtain this upper bound by choosing S equal to 1.5. So we consider two limit regimes. At low SNR, the tightest divergence, so the cube coincide with the Bhattacharya upper bound. And at contrary, for larger SNR, the S star, so the optimal S parameter, is close to 1. So in this case, the Bhattacharya upper bound is a losing bound in this regime. So in this graph, we can see S star versus the SNR. And for lower SNR, we can see that S is close to 0.5. And for higher SNR, we can see that S grows to 1. And in blue, this is numerical optimization, and in red, this is the analytical solution. So, I conclude. So the first point is the derivation and the analysis of the performance in terms of minimal base error probability for the detection of a random core tensor. The second point is the error exponent and the optimal S parameter for the detection of a tensor X that follow a higher order SVD. And this expression, so the analytic expression, can be interpreted in the context of the random tensor theory. And the random tensor theory is an extension of the well-known random matrix theory. And finally, an important conclusion of this work is that the Bhattacharya hyperbond is the tightest bond at low SNR, but at contrary, this property is no longer true for higher SNR. Thank you.
Today's topic is coordinate-wise transformation and Stein type densities. This is the outline of this talk. Let me consider a set of density functions obtained by coordinate-wise transformations of a given density. And let me call it a fiber. And then define Stein type density as a by a functional identity as stated later. And then I will establish an existence and uniqueness theorem of the Stein type density in each fiber. And finally, discuss application to a rating problem. Here is a picture of this talk. In the space of probability densities, if we are given if the probability density function P is given, we have a fiber by coordinate-wise transformation, and each fiber has a Stein type density. Okay, let me give some definitions. First, let script P be the set of positive and continuous probability density functions on the Euclidean space RD, such that the mean of each coordinate is equal. The last condition is not so essential. We call a map T from RD to RD as a coordinate-wise transformation if it is written like this. So the map T, each coordinate of T depends only on that coordinate. So this is a coordinate-wise transformation. And for each density function P, let me define the P fiber by this formula, script FP, which is a set of push-forward density of P by the coordinate-wise transformations T. Okay, and there are two remarks here. The set FP is totally geodesic subset in the Wasserstein space, and the secondary, the fiber has a unique copular density, which is known as Sklar's theorem. And next, we define an energy functional on the set of probability densities. The function is defined by this formula. The first term is negative entropy, and the second term represents the internal energy, where b of x is a continuous function of x. And this functional appears in the theory of optimal transport. Sorry. And here is a simple lemma. It is not difficult to prove. The functional E has the minimum point in the space P if and only if this integral is finite. If this condition is satisfied, the minimum point is given by this one, the exponential family. And we consider the case here, this condition is not satisfied. The integral is infinite. Then the infimum of the functional E is minus infinity. Here is a picture of our setting. The functional E is not bounded from below on the whole space P, but this functional may be bounded from below on each fiber because the fiber is a proper subset of the whole space. Okay, this is the problem. To minimize the functional E of the fiber, consider a perturbation of the transformation. Epsilon is the identity map plus some perturbation. Here epsilon is a small number and f is an arbitrary function. Then we have, as epsilon goes to 0, the first variation formula. And so if this term vanishes, then that point is the minimum point of E. Now we define the Stein type density. A density function P is called a Stein type density if it satisfies this equality. This is the first variation. And the Stein type density is named after the Stein identity, which characterizes the standard normal density function. And this identity is used for evaluating risk of estimation and checking discrepancy from the normal distribution. Okay, now to state our main theorem, let us suppose some conditions. First, we assume that the function B is degenerated as follows. Vx is a function of sum of its coordinates, where psi is a non-negative and convex and coercive function like this. And please note that in this case, the integral here, integral is infinite because the function B is degenerated. But this restriction can be relaxed, but we assumed anyway. For the second assumption, we assume copositivity for the density function. Here, for each P, density P, we denote the product of marginal densities by P independent, like this independent density function with the same marginal. Then we say that the density P is copositive if the following inequality holds. This is some infimum of the ratio given by this. And if P is the independent density function, then this quantity is 1, so it is copositive. And sufficient conditions for copositivity are discussed later. Now I'd like to state our main theorem. Assume that the density P is copositive, just defined. Then there exists a unique Stein type density in that fiber. And this is the main theorem. Here is a brief sketch of the proof. Details are omitted, but for uniqueness, the displacement convexity argument in the theory of optimal transportation can be used. And for existence part is more essential, important in this talk. And for existence, we use the positivity condition. And by using the copositivity condition, we obtain the following inequality, and the problem is essentially reduced to the independent case. This is the rough sketch. Now, we give some sufficient conditions for copositivity. The details are omitted. The notion of positive dependence plays an important role here. There are, here I show 3 conditions on positive dependence. And here is the result. It was known that MTP2 condition implies associativity, and it implies PSMD condition, and finally it implies our copositivity condition. And MTP2 condition is relatively easy to confirm, so this condition, this theorem will be useful. Okay, finally, I'd like to discuss an application of our results. The problem is here. Let x1 to xd be random variables with density function p, which represent students' scores on the academic subjects. Okay, and how to classify the students into the superior half and inferior half. The answer, one of the answers is here. Let psi x is absolute function and t be the Stein type transformation of, so the t sharp p is the Stein type density of p. And then define g, random variable g, by the sum of transformed variables. Then our main result implies the following stochastic ordering property. Given that this conditional probability is always greater than the right one. And this, the interpretation of this inequality is the students with larger g are superior. Okay, here is a numerical example. What it is further, it is a little artificial. Okay, anyway, in summary, we showed the existence and the uniqueness theorem of Stein type densities under the copositivity condition, and an application to rating problem was presented. And there are 2 conjectures and some further topics here, so please, if you are interested in, please ask me. Thank you very much.
So in your ordering, the alpha is an hyperparameter?
Alpha is real, any for Thank you very much.